Okay, so we have this reaction, nitrogen monoxide and oxygen and carbon monoxide reacting to form nitrogen dioxide and carbon dioxide, and we're asked to determine the orders of reaction with respect to nitrogen monoxide, oxygen and carbon monoxide. Now the stoichiometry of our equation, you'll notice, is a 1:1:1 ratio there, but that doesn't tell us the orders of reaction. For that we need to look at the experimental data, and that's what we have here. You'll notice that we have initial rates of reaction and initial concentrations and the initial rate of reaction. Now we have that because we may be following this rate by monitoring the change in the concentration of one of these species, but the other two species we certainly don't know the concentrations of at any point apart from the beginning of the reaction. So that's why we're looking at initial rates for this. And what we're going to do is we're going to compare a series of runs. Now we have taken these runs where we're keeping the initial concentrations of one or two of the reagents constant and varying just one. And by comparing two of the runs we should be able to determine orders of reaction of at least one of the reagents. So let's follow this and let's take nitrogen monoxide to begin with. Now what we want here is a change in the concentration of nitrogen monoxide, but a variation in the concentration of the concentration of oxygen and carbon monoxide to remain constant. And you'll notice runs 2 and 3 follow that criteria. You can see that the concentration of NO is doubling, the concentration of oxygen and the concentration of carbon monoxide remains constant. So we can compare runs 2 and 3. We double the concentration of NO and the concentration of O2 and CO are constant for this. And you will notice that the rate of reaction doubles. So therefore what we can say for this case is that our rate is proportional to the concentration of NO to the power X in some way. It's not proportional to for any change in the concentration of oxygen and CO because they're remaining constant here. And if we double the concentration of NO, the rate doubles, then it's directly proportional. Put it up a little bit. In other words, it's first order with respect to NO. So, now let's consider oxygen. Now here we need to compare two different runs. You'll notice runs 1 and 2 follow for this. You can see that if we compare runs 1 and 2, concentration of O2 doubles and the concentration of NO and carbon monoxide are constant. Okay, so let's have a look and see what happens to the rate of reaction. You'll notice again it doubles, so therefore we can say the rate is proportional to oxygen concentration to the power, let's say Y in this case. A doubling of the concentration produces a doubling in the rate of reaction, so that is going to be equal to, therefore rate is proportional to the concentration of O2 to the power 1. In other words, again it's first order. With respect to oxygen. Finally, let's take carbon monoxide. Now with carbon monoxide, you can see, let's just move that up a little bit like that. That's it. Let's just compare two runs where we're changing the concentration of carbon monoxide and keeping the concentration of oxygen and nitrogen monoxide constant. You can see runs 1 and 4. Are the ones to look at. Here, the concentration of carbon monoxide doubles, but the concentration of NO are constant. What happens to the rate? Nothing. Therefore, when we look at our rate expression, in this case, it's 0 order, because there's no change in this. So it's 0 order. Carbon monoxide.